everyone. In this video, we present our project titled Efficient Image Generation with Sana. This project is based on the Sana architecture, a modern diffusion-based image generation framework designed to generate high-quality images efficiently. In this presentation, we will explain the base paper Sana, describe our contributions, show results and improvements, and then summarize key takeaways. So, coming on to the base paper, what is Sana? The base paper SANA is a efficient high-resolution image generation with linear diffusion transformers proposed in 2024. The main goal of SANA is to make high-resolution image generation faster and more memory efficient while maintaining strong visual quality. The traditional diffusion models are powerful but computationally expensive due to quadratic attention complexity, large number of tokens, and high memory requirements. SANA solves these problems through several innovations. The first major component is the deep compression autoencoder. Traditional models compress images by 8 times, but Sana increases this compression to 32 times. This means 16 times fewer latent tokens, lower GPU memory usage, and faster training and inference. The core motivation of this is that the 4K images have more redundant information and thus can be more compressed. Even with such strong compression, Sana maintains image quality using multi-stage training and larger channel capacity. This component plays a major role in enabling high-resolution image generation. Coming on to the second component, traditional attention mechanisms scale with a big O of n square complexity. This becomes extremely slow at high resolutions. So Sana replaces this with the linear attention, which reduces complexity to big O of n. This significantly reduces the computation cost. However, linear attention can lose local spatial information. To fix this, Sana introduces the mixed feed-forward network. This module adds a 3 by 3 depth-wise convolution layer which and local feature recovery, improving the spatial understanding. Another important innovation is that Sana removes positional embeddings entirely. This is called no positional embeddings or NOPE. Despite removing positional embeddings, the model still maintains strong performance due to the mixed feed-forward network having this 3 by 3 convolution depth layer. The next component is the decoder-only LLM, the Gemma 2. So the Sana replaces the old T5 text encoders that the normal diffusion models use with Gemma 2, a modern chatbot style model that actually reasons about your prompt before generating. Due to this reasoning quality, we get a better text enhancement which other diffusion models lack. The next core component is the flow-based training. Instead of predicting noise like traditional diffusion models, Sana predicts velocity using a method called rectified flow. This improves training stability, sampling efficiency, and convergence speed. Sana also introduces Flow DPM Solver. This reduces the number of sampling steps from around 28 to 50 steps, coming down to 14 or 20 steps. This makes image generation significantly faster without losing quality. To summarize, the base Sana model achieves high resolution image generation, reduced computation cost, faster inference, and efficient memory usage. These improvements make Sana suitable for consumer GPUs and edge devices. Now moving on to our contributions. Our project extends Sana with three major improvements. First is the training from scratch on Celeb A dataset. Next is the integration of adaptive flow DPM scheduling. And the last is the sensitivity based block pruning. Our main focus was extreme inference acceleration for edge device deployment. So, the first contributions training from scratch on Celeb. We used the Celeb dataset which contained around 2 lakh face images. So these images were encoded using the autoencoder and converted into a 32 cross 32 latent grids. Then this was trained for the Sana 0.6 billion variant on a single NVIDIA T4 GPU. This helped us to validate the efficiency of the architecture on real-world datasets. The next contribution is the integration of the adaptive flow DPM scheduling. In the original Sana models, sampling steps were fixed, but we observed that not all time steps are equally important. The most important image features formed during the middle time steps around zero point 0.4 and zero point 0.7. So we introduced velocity aware adaptive scheduling. Instead of fixed steps, our method dynamically adjust step size using the velocity magnitude. This means more steps were needed and fewer steps were redundant. As a result, we reduced the number of function evaluations from 20 to 12 steps and achieved a 6.6% latency reduction without noticeable quality loss. The next contribution is the use of sensitivity based block pruning. The large transformer models often contain redundant layers. Some layers barely change the output. We identify these redundant blocks using the block importance score. This score measures the cosine similarity between input and output activations. If the similarity is high, the block does very little. So we remove the 8 low importance transformer blocks. This reduced the model depth from 28 to 20 blocks and reduced the parameters from around 591 million to 426 million. After pruning, we fine-tuned the model to recover performance. Results showed around 27.9% model size reduction, 20% inference latency reduction, and a 24.8% throughput improvement while maintaining visual quality. Here is a visual comparison of the images generated by the original Sana baseline model and the adaptive pruned Sana that we fine-tuned. As we can see that the key facial structure and visual consistency is preserved despite the 27.9% parameter reduction. Our final architecture looks something like this. The linear diffusion transformer block are reduced to 20 from 28 and we integrated the adapted flow DPM scheduling. Now that we have explained the base model and our contributions, we will move on to the experiment results and demo outputs.
Now I will demonstrate the adaptive DPM solver that we have implemented on top of the SANA paper and which is implemented here in the DPM solver script. And I have prepared this latency.py script which will test both and will write the logs in latency.txt. First, I will run the flow DPM solver. It will take around a minute, so we will have to wait. Okay, it is run. Now we will run it for adaptive flow solver. Okay, it is also done. Now we see in the latency.txt, the first one was flow DPM solver with had the latency of more than 10 seconds for an image, And in adaptive solver, the latency was reduced to 9.65 seconds per image. Thank you.
Hello, I'm Neeraj and I'm going to demonstrate block impedance tuning applied to the SANA 0.6 billion diffusion transformer. The goal is to reduce model size and improve efficiency while maintaining image generation quality. So during training, the baseline model used 11.6 GB of VRAM per step, and after applying block impedance tuning and removing the 8 least important transformer block, VRAM dropped to 10.36 GB, which is a 10.7 reduction, and training time improved by 1.23 times. Let me show you the block impedance chart. This chart shows the impedance score of each of the 28 transformer blocks, and the red bars are the blocks selected for removal based on the low quotient similarity between input and output, meaning they contribute least to the model's computation. Now I've already run the demo baseline and demo modified script. A baseline script uses the baseline model, that is the unpruned model, to generate the images, and modified one uses the pruned uh, model to generate the images. So from the statistics, you can see that the pruned model is better in terms of latency and VRAM uses as compared to the baseline non-pruned model. Let me show you the output images. This is the image which is generated by baseline output. Uh, it is loading, and this is the image that is generated by the modified model.